Okay, we were doing Routh-Hurwitz analysis and tabulating the Routh-Hurwitz array, and from there determining several things. Things were fairly simple if you didn't get a zero in that first column. So let me talk about those cases because to me, I think I consulted at least 3 textbooks, and all 3 were, I'm going to say, pretty inadequate in in stating how to deal with these situations. They had some of it, but not quite thoroughly. First, there's 2 cases of these special cases. Case one is when you get a 0 in that left column, but entries to the right in that same row are there's some non-zero terms. So it's a 0 in the left column, but not all zeros in that row. Second case is all zeros in that row. Either way, I'm going to state unequivocally, 99% sure this is true, that if that case, it's not going to be stable. It's either going to be marginally stable or unstable. You should look for right half plane poles, because if you find any by using the Routh criteria, then it's not stable. And a subtlety is if you get an all zero row, you really should look at the auxiliary equations if it turns out to be in a row higher than s to the 1. Because that could mean repeated poles on the imaginary axis. And these guys are kind of hard to find. I think that's why a lot of textbooks just forget to even talk about it. So here's how to handle the case 1. We have some non-zeros in the same row as where the 0 was in the left column. You replace that 0 in the left column with some epsilon. Finish your Routh array using epsilon. Then when you're all done, take the limit as epsilon goes to 0. If doing that, you don't get any right half plane poles, then it's marginally stable. Not stable, it's got a 0 in the left column. Here's an example. Here's, let's see, Routh array is going to be 1, 2, 6. And the second row is going to be 3, 6, 9. 6 minus 6, you get a 0 right there. We're going to replace that with epsilon. Do that, so then you got to do this arithmetic. Let's see, what's going to go here? It's going to be 6 epsilon minus 9 divided by epsilon. Bring this 9 down, etc. I'm not going to go through all that. It's a little bit tedious. And when you're all done here, then you take those limits. I'm going to say you get this. Take the limit of epsilon from the right, meaning positive numbers. So consider this as a positive number. Then you get something negative, and you go back to positive again. Just like before, that means 2 poles in the right half plane. This is a case where this system is unstable. It's not marginally stable, it's not stable. It is unstable. Okay, what about the row of all zeros? We've actually done that before, and we found we assumed marginal stability pretty much, and we found the frequency of sustained oscillation. We actually kind of skipped some steps. And a lot of what I'm telling you, I more or less skipped it, not just like the textbooks do. I skipped it pretty much in my courses. I didn't give students troublesome problems. Any problems I gave them, they could assume marginal stability and find the frequency of oscillation. But here's yet another example. I'm not going to go through it. You get the row of all zeros in the S1 row. What you should do, which I didn't do in the previous examples, is replace this row of all zeros with the derivative of the auxiliary equation. its auxiliary equation. Its auxiliary equation is 3s squared plus 12s to the 0. 3s squared plus 12. You take its derivative, you get 6s. So we're going to replace that 0 with 6. Actually, a 1 would be good enough. You can always multiply any row by some constant other than 0, and it's okay. When we do that, we get this Routh array. I just replace that row with that 6, and I get all positive terms in that first column. So no sign changes. So certainly no right half plane poles. Could there be double poles on the imaginary axis? I'm going to, spoiler alert, I'm going to say no because it happened in the S1 row. Its auxiliary equation is only the S squared. You're only going to get one pair of complex conjugate poles there, not a repeated pair. And MATLAB does compute the poles, 3 purely negative in the left-hand plane, and complex conjugate, in fact, imaginary conjugate poles right on the imaginary axis. If you look at this, you get 312, divide both by 3, you get 1, 4. You did our find the state oscillation, you get omega equals square root of 4, 2, and that's where it's going to be on the imaginary axis. That omega is where it crosses the imaginary axis. I don't know if I said that before. Here's another example. There's the characteristic equation. Start our Routh array. We get all 0 row up here in the S cubed row. It has this auxiliary equation from here. 1s to the 4th, 2s squared, 1s to the 0, which is this. Take its derivatives, you get 4s cubed plus 4s. So we replace the all 0 row with these 2 4s. Could have been 2 1s, 2 4s. And continue on down. And up, get another all 0 row. Its auxiliary equation comes from here, which is s squared plus 1. So its derivative is 2s. Replace that all 0 row with that. Continue on down. And we get all positive numbers again. So no right half plane poles. That much is true. Is it marginally stable or unstable? Remember the auxiliary equation, the roots of the auxiliary equations are roots of the overall characteristic equation. Here's the auxiliary equation. Here's what it means. It's in the S4 row, S to the 4th row. So that's S to the 4th, 2s squared plus 1. Oops. Typo, that should be an S squared there. Which is s squared plus 1 squared. The roots of this are plus and minus j again, but it's a repeated root due to the squaring of it. So you have a repeated pair on the imaginary axis. This system is unstable, even though it had no poles in the right half plane. And like I said, this kind of nuanced case is not explained well in textbooks that I found. I kept it simple for my students. Any all 0 row was in the S1 term, S1 row, and they could assume marginal stability and go ahead and calculate sustained oscillation. Once you get a row of all zeros, you know it's either marginally stable or unstable, but it's not stable. What you should do is use the derivatives of the auxiliary equations to continue doing the Routh's array to see if there's any poles in the right hand plane. I didn't do that in my previous examples. If you don't find any, the system might be marginally stable, but it might still be unstable. Depends on the auxiliary equations. And I could say you're good if that row of all zero is in the S to the 1 row, because you're not going to get, if that's the only all zero row. If the all zero rows are not above the S1 row, then you're going to get marginal stability if there's no right half plane poles. That's an S squared equation. You can't get repeated complex roots with a second order equation. Roots of the auxiliary equation are equations are roots of the original characteristic. Look at this example we just did. We got an auxiliary equation here. It was this one, an auxiliary equation here. So there are two different auxiliary equations. In this case, they came up with the same roots. This one came up with repeated roots. Same root is down here, but repeated. Anyway, that's it, and that's kind of the most subtle part of all the Routh-Hurwitz. Don't have any zeros in that first column. Things are pretty easy. And that ends it for stability and Routh-Hurwitz.